Now, we already know we had this form for arc length and parametric form, dx dt squared and dy dt squared dt from a to b, whatever values we had for t. And we saw how using that we could convert to, in polar form, that it looked like this. We'll say alpha beta, and then we had this. We had f of theta squared and f prime of theta squared d theta. So we ended up with that. Now, if we start off with, and remember this thing came from this, I should say this is T0 to T1. This is A to B. This started off 1 plus y prime squared dx. And that, when in parametric form, became this, and in polar form became this. You have a similar progression from the 2 pi. We'll start off with r of x, and then 1 plus y prime squared dx for surface area of a surface of revolution. Okay, surface, the area of the surface of revolution is what I want to say. So you have a similar progression that takes you back and forth in here. And this one is that, remember that 2 pi, this time T0, T1. And we've got the, in this case, that R, which is, well, let's just say we're depending on which axis you're revolving around, let's just say that I want this to be y in here. And then I had, again, my dx dt squared, the dy dt squared, like that. And then this is, sorry, this, where is it? Okay, that is t, sorry about that. That's with respect to t, and this function over here, y, would have to be a function of t. And of course, this would be this function. The function that you use here would depend on which axis you're revolving about. If it's revolving about the x-axis, then you would use y. If it's revolving about the y-axis, you would use x of t. So it's either y of t or x of t. Now, then this thing can be converted with a little bit of work. Not much. It turns out the same transition that we made to get from here to here is also used over to get from here to the next one. And this one's just going to be 2 pi. And again, depending on the axis of revolution, if I stay with that y, to remember y equals r sine theta, or f of theta sine theta. So this would become f of theta sine theta. And then we'd have that square root of the f of theta squared, and then the f prime of theta squared, all d theta. Sorry for running out of room there. But you see a nice similarity between the formulas as you go from one form to another, parametric form, and then to the polar form. Okay, it's a nice movement from one to the other. You see and the analogous changes from one form to the other. It's sort of stay with you. Okay, these two kind of pair up, these kind of pair up, and these over here. Okay, the progression from one to the other is what's important. So you gotta, so we want to try to remember that. Now let's look at an example. So I just wanted to bring that up. I'm not going to derive this formula because I almost did here if I went from this form to the surface area. We got that extra factor in the front there. That's your distance to the axis of revolution thrown into this formula along with the 2 pi. Otherwise, it's the same formula. So you've got the arc length, and then you're multiplying it by the distance, the radius, the distance to the axis of revolution. And that gives you the surface area along with the 2 pi. Okay, now let's take an example. Well, we got example 6 now on our handout. Oops. Okay, let's see. It says find the surface area by revolving r equals 6 cosine theta about the polar axis. Okay, r equals 6 cosine theta. Now you might, after working with these, you might recognize what that is. It's just this circle here, centered here at 3, and it's all the way out to 6 there. Okay, so it might take a little bit of doing on your part to make sure you know what that graph looks like. But now it says we're going to go from 0 to pi over 2. So we really don't need the bottom half then. Okay, so let's get rid of the bottom half. Whoops. Didn't mean to get rid of all of it. Okay, so this will be revolved about the polar axis. So it's coming around this way. So it's basically generating a sphere with radius 3. And we already know that's going to be 4 pi r squared. Surface area of a circle with radius r. So we're looking for this number, 4 pi times 9, 36 pi. That's what we should get. But let's see how it works with our formula. Okay, so our surface area will be 2 pi. And we want the distance to the x. So we're going to have y of theta. Well, should I call it that for now? I guess I could. Y of theta square root. Now we want 36 cosine squared, okay, plus 36 sine squared. That's since the derivative, remember, r prime would be 6 or minus 6 sine theta. So when you square it, you get the disappearance. And we're going from 0 to pi over 2. So the negative disappears in there. Now inside here, you get a nice result, and I'm going to put in that y value, y of theta. Okay, remember y was r sine theta. So it's 6 cosine theta sine theta. So that's what I have here. I've got 0 to pi over 2, 6 cosine theta sine theta. And this is just, well, all of that's gone because, I mean, I guess got the square root of this and got a 6. Okay. So I've got another 6 in there, don't I? 6 out of here comes out in front as a 6. Okay, so it looks like I'm coming up with 72 pi on the outside here, and on the inside I just have 0 to pi over 2 sine theta cosine theta. Okay, now that's nice because the derivative of sine is cosine. I've got u to the n du right here. 72 pi sine squared theta from 0 to pi over 2. Over 2. Sorry. Okay, and then that's 72, well, okay, 36. 36, going to get rid of the 2's here, 36 pi. And then we have sine squared pi over 2 minus sine squared 0. So that is 36 pi times 1. And there's a 36 pi. So I know it's, you know, not earth-shaking result here, but it does illustrate using the polar coordinates to get our results. To get this result in rectangular coordinates, it would be, I mean, if we didn't know it was a circle, it would be difficult to integrate. We kind of, since you're working with a circle, there might be some ways out of there, but if you run up against some difficulty. All right, I just wanted to mention something at the bottom here. Okay, we finished that up there, and had you been working in rectangular coordinates, this is the equivalent equation in here that I've switched back into first, second step, third step, fourth step, and here I solved it for y. And of course, I already knew that it was a circle with on the x-axis in the center at 3, 0, but so I went as far as I had to, and I solved this for y here. Here I found a derivative, and then I used my form from the first one we encountered for surface area for us, surface revolution, 2 pi, and then notice I've got the distance to the x-axis here, that's the y, and then over here I've got 1 plus y prime squared in here. So I found y prime and then I squared it. Now this, fortunately, this all simplifies to just this, which gives us a 36 pi at the end here. Okay, 36 pi. Okay, so it's kind of neat to see the two methods. You're not always able to get this done as easily in one system as is the other. This one looked about the same amount of work either way. But sometimes making that switch into polar coordinates is a better way to go in terms of how easy the integration is. Now, if you're just putting everything into a calculator or a computer program, then it isn't going to make that much difference. But, so there's a nice little review down here of using that our original formula for surface area for the revolution, this one here. Okay. Anyway, okay, so that's about it for this one then.